Well, hello everybody, and thank you for attending another one of the Siemens Sinumerik-based webinars. Today we're going to be getting into some more advanced turning topics. This will be specific to ShopTurn programming, but this is looking at machines that have sub spindles or counter spindles. So we're going to get a chance to dig into all the nuances of dealing with a machine with that type of technology. I am your presenter, Chris Pollack. I am the Virtual Technical Applications Center Manager. That is a very fancy title for a new department we've created that is concentrating heavily on this web-based content. So not only am I going to continue to promote these webinars as you guys have seen, but we're going to be developing a lot more digital web-based content. So keep your eyes out for that. We're going to start to get into doing how-to videos and a bunch of other stuff. So pretty exciting. I am always here as a contact for you guys. So if you have any questions or you need any insight into the Sinumerik world, please by all means reach out to me. My contact information is on the screen. I would say probably email is the simplest way to get a hold of me. But if you're in a bind, by all means, please feel free to reach out to me. So we got a few new webinars coming up in the not-so-distant future. Just to kind of give you an idea of what's coming down the road, in December, we're going to start to get into part probing. And this will be a first. We haven't really got a chance to delve into the probing topic at all. So this is probing in auto mode. That means that, I'm going to have a probe in the machine spindle. I want to be in a run mode, and I want to come down. I want to start to qualify my part. So whether it's a case where I'm just trying to align a fixture, or I want to adjust a datum, adjust a work coordinate, we're going to talk about some of those topics. After that, we're going to go back and revisit some earlier content. So we're going to do a shop mill webinar specific to conversational programming and milling. So for those of us that maybe are new to the Siemens technology, you'll get a chance to show some of the more basic side. I have a tendency to get into a lot of advanced content, but we can't lose sight of some of the more entry-level material. So we are going to do a conversational programming shop mill event in January. And then in this series of higher technology lathes that I've been trying to, do a webinar every few webinars, I've been trying to kind of move along the content of what we've been doing in the turning side. We're going to start to look at a B-axis mixed technology lathe, so a turn lathe. So it's kind of building off the building blocks of the previous webinars. So imagine this, this machine that we're working on today, but now we'll have the option of having a B-axis, so the machine could actually do full 5-axis contouring. Okay, so all the webinars can be seen, and you can always register for the next upcoming webinar or check out any of the previous webinars recordings, because they're all categorized there. Right here from our CNC for You website. So the link is on the screen. Additionally, you can drive straight to the webinars with the /CNC-webinars link. But just get the CNC for You. You can click the webinars. There's a lot of good material here, a lot of other additional content that's certainly worth checking out. And one of them is the fact that we host in-person CNC training at our technology center out in Chicago. So if it's something that you guys think you can certainly join, please feel free. Give me 1 second. One of our attendees is having trouble with the auto. Okay. So with that being said, if you come over to the CNC training section, or you can use the direct link you have up in front of you, check out some of the classes that we offer out in Chicago. We have 3 different operation programming classes. Goes all the way up to full 5-axis programming. I happen to host that one specifically. It's a great program. We don't charge anything to come to attend. They're 3 to 4 day courses, and we get into a lot of hands-on work. So if you could, we'd love to have you guys come out and join us for one of these classes. So just check the website. You'll get the list of upcoming classes, what the dates are, and you can register right from there. You click on the link. It's going to pop up a little registration sheet, fill it out, and then you register for the class. Okay, so today we're going to talk about two specific platforms, or the content, shall I say, will apply to both of our primary platforms, which is the 828 and the 840. So everything you see here could potentially function on your 828 or your 840. Obviously, there's options that are required, also hardware from the builder's perspective to make this kind of stuff work. But these are to be the two control platforms that the content or material we're talking about today is linked to. So today's topic, again, I mentioned it briefly, but we're going to start to talk about machines with Sub Spindle and trying to utilize this technology and try to make it as painless as possible. I mean, it's an advanced machine. You got a lot going on here, but I think as you see it, it's summed up pretty simple. So first thing that I always like to talk about when I get into these advanced machines is kind of what you're going to see from a display perspective. What is the screen going to look like? Where are you looking for information? I mean, that's all important pieces of this puzzle. So once you have a machine that has multiple spindles on it, you're going to see that you're going to get a few extra axis displays and potentially axes on that machine. So if you look on the left side of the screen, we're not only going to have our linear axes for X and Z. Quite typically, a machine with a sub spindle would normally have a Y-axis as well. But you're going to have multiple spindles on this machine. So we're going to have our main spindle. That could be designated, in this case, our example, we have it designated as SP1. But this could be anything. You know, it's really up to the OEM what he wants to call the spindles. We have a live tool spindle. That's going to be our SP3 spindle. And then our sub spindle, that's going to be treated as the Z2 axis. That's going to be the linear axis that drives the sub spindle. Additionally, we'll have the SP2, and SP2 is referring to the spindle on the actual spindle, so the rotating spindle on the sub slide, shall we say. This is where we're going to start to see the information. So in the little work display position, if you don't see all the info right up front, there is that scroll bar. So if it doesn't quite all fit, we try to obviously give you the info that you really need to see the most, which would be obviously your X, Y, and Z coordinates. And then you can scroll up and down to get access to the other displays. Now, when looking at this technology, it's good to start to get your head around what the layout and the axis designation would look like on that type of a machine. So on the right side, I just gave a typical layout of a machine that has a main spindle and a sub spindle. These would be collet spindles in this case. Has a little parts catcher there for us. And you can start to see the axis designation. So our X, Y, and Z associated to our turret, and then certainly C1 would be our left spindle. In this type of machine, that's a fixed spindle, so it doesn't move, just spins. And then we have on our right our Z, our case before we were talking about Z2, that would be our sub spindle, and that can be slid or positioned over to the main spindle for doing part grabs. And that's the big thing we're going to talk about today, is really how do I handle part transfers, part cutoffs, how do I work with this sub spindle. Now, it's really important to start to understand where all the datum referencing comes from when I'm dealing with this type of machine technology. So machine 0 is built off of the face of the primary or the main spindle. Now, it's very possible that your machine has to go reference itself. Maybe it has incremental encoders, or the builder just forces it to go to a predetermined reference position. Well, that's still going to be based off an offset of the main spindle. So if you start to look at how all your zeros stack or your offsets stack, they're going to be stacking up off of the main spindle. Now, from a tooling perspective, the turret is going to be datumed in relation to that main spindle, and there'll be a fixed location on the turret that is its primary 0. So the tools, as we get into using the tool offsets, are going to be physically the distance from a gauge line or the turret datum to the tool tip. So instead of seeing large offsets like we typically would on a simpler technology lathe, it's quite common on a basic 2-axis lathe that you'll see the offset from the machine datum position to wherever you're setting the 0 on the part. So there'd be large offset values. On these machines, we're going to see smaller offset values, and that's going to be the distance from the mounting surface to the cutter tip. And we're going to talk about that a little bit more here because it's an important concept to start to understand. So what is this machine layout, the machine we're specifically going to be looking at? So our machine has an X to Z axis. That's going to be controlling the turret. So the turret will be moving around independent of the two spindles. We have 3 physical rotating spindles. SP1 is my main spindle, and that's again a fixed spindle, so that doesn't move linearly. SP2 is going to be the sub spindle or the counter spindle, and that one can be driven on the Z2 axis. And then SP3 would be a live tool up on our turret. Now, as you start to have multiple spindles, you're going to ask, well, how do I view what those spindles are doing, and how do I drive them, just for something as simple as, well, I want to start up a spindle and run it. So in the TSM screen, right there in jog, you'll have the now ability to be able to toggle through your multiple spindles. And this is going to match whatever the builder decides to kind of name those spindles. So in our case, we have spindle 1, 2, and 3. So as long as I select that appropriate spindle, then any of the commands I give it in the RPM field or the M-code field would drive to that spindle and allow me to fire up that spindle. Additionally, if I want to see feedback from the spindle, I can just click on the S1, S2, or S3 field in the TFS window, again still in jog, and then I'm going to get the display of that specific spindle and what that spindle is doing. So let's start to put some real numbers to this, and this is going to be an important diagram moving forward. We'll reference this a few times during the webinar. This hopefully will kind of get your head around the layout of this machine. Now, I intentionally wrote this webinar in metric, specifically because it's easier with metric. There's a lot more round numbers. So whether you're running the machine in inch or metric, that's kind of an irrelevant point. The bigger thing is just to understand where these numbers are coming from. So our datum A, which would be our spindle face, our main spindle face, that's where all of our dimension data is going to come from. So first thing I see is our 1,000 millimeters. So what that's going to be treated as throughout our part programming scenario is that's going to be the retract position or safety position we send the sub spindle back to. So that'll be where it goes at the start of the program. It'll be where it goes back to when I go to start doing some machining. Now that could be the max travel of Z2, but it doesn't have to be. It's just important for you when you come up with a plan of how you're going to start to use this machine and where you want things to move to, you want to kind of give yourself a known location that you can work from. Additionally, we dimension the turret coming off of that spindle face at 500 millimeters in Z and then 250 millimeters linearly in X. So this I'm going to use as a safety retract location. So you want to make sure you pick a safety retract location that's going to be completely clear of that Z2, that sub spindle sliding back and forth. Last thing we want to do certainly is be able to catch a tool while we're doing our transfer section. Now, the input is typically going to be set to diametric for X. So when we actually type in the value, you'll see I'll put 500 millimeters for both, but it's physically 250 millimeters away from the center line. Now, in addition, we're going to need to know some information about the work holding. And we're going to see here in a sec how do I start to plug that into the control. But it's important that you know the chuck body size and the jaw projection size. Once you have those, you're also going to need to know where you would want to have the part sitting in those two clamping orientations. So how far out do I want to stick it for this job? And then when I go grab it, how far out do I want it to be sticking when it's all said and done? So how do we set this machine up? Well, what you're going to do with a sub spindle machine is you're going to use 2 separate work coordinates. Really doesn't matter which numbers you use or sequence of numbers. I started at 54 and went to 55. I could have used 58, 59. I could have went, higher to lower. Again, the order doesn't matter. They can jump between the two. The important part is I'm going to pick 2 work coordinates. One work coordinate is going to represent my main spindle. In this case, it's going to be G54. And the other work coordinate is going to represent my sub spindle. In my case, it's going to be G55. So if you notice, we're looking at G54 right now, and I have a Z value of 185 millimeters. So all that's doing is it's saying, okay, that was where we expect the front of the part to be from the spindle face. That's why I have that large positive shift. That's about all that you're going to need to put in here for the work coordinate scenario. Your tool offsets will obviously manage where the tool is in relation to the datum of the turret. Now, additionally, we're going to have to set up the second work coordinate, and that is going to be the sub spindle. So the sub spindle, again, it's still a value based off the main spindle. Here we have a larger number, 795, and you'll get to see how these numbers created as we get to a live demonstration. But the important part here is not only the offset value, but how we're handling the z-axis. So if you notice, under the z field, if you go to the details of the work coordinate, so it's easy to get to. When you're on the work coordinate level and you're highlighting it, there's a vertical soft key called Details. If you press that Details button, then you're going to come in and you're going to see this detail screen. Well, what you want to do is you want to put a checkbox in the Z mirror field. And what that's saying is whenever G55 is called up, my Z is going to be mirrored or pointing in the opposite direction. So any motion towards my part, anything that's cutting into my part, is always going to be a negative value. Now the physical motion is going to switch, but it's always going to be a negative direction when I'm moving towards the part. The beauty of this scenario is I don't have to keep thinking in my head, gee, which of the two spindles am I working on as far as which direction I'm telling my Z to go. You know, that's always a challenge when I don't have that ability of mirroring the axis. I got to always remember, okay, I'm on the sub spindle, so I got to be moving plus while I'm turning or drilling my part, or on the main, I got to be moving minus. But the other thing that's really beneficial here is the fact that I can use common routines between my two spindles, and I don't have to reprogram them. So the same toolpath that works on the main will work on the sub, because the negative directions are always going towards the part. Now, a good question came in from Jay. Does the Z direction affect the turning direction of the spindle? No, it should not. It should only have an effect on the physical linear motion of the Z axis. Okay, so from here, now we got to talk about the chucks, right? We got a basic handle on the work coordinates. We know we're going to use G54, 55, but we do have to set up our chucks. So there's a screen that you can find in the parameter screen under setting data and spindle chuck data that allows you to set up your work holding. And this becomes very important because we're going to use these numbers to be able to determine where the part is, where do I drive my sub spindle to do my handoff. So you can see there's a lot of values that all get figured out for you here, but it's all based on these numbers. So what you want to do is you want to have an accurate measurement of your chuck body and an accurate measurement of your jaw projection. And then you can flip that around. And, you know, the jaw projection you're going to adjust as you put different work holding on the machine, obviously. As long as you're not swapping out the chuck body dimensions should stay at constant. So my machine, just for simplicity's sake, I'm using the exact same size chuck on my main spindle and my sub spindle. So my chuck body and my jaw projection happen to be the same number. It's pretty common that these are not the same values. So you're going to want to make sure you have accurate dimensions for both. So you see we got our chuck body dimension. In this case, it happened to have been 89 millimeters. So I have that input into my ZC1 or my ZC2 fields. That's the body dimension. And then I have my jaw projection. So this one happened to be 51.625 millimeters. So that's the value I plug in here. So just to show you real quick, when you're in the machine, right, all you have to do is go over to, I'm just going to put my enables on. I just fired this machine up. Go over to the offset screen. Make sure you go to setting data, the button in the lower corner of this display. So it's a horizontal soft key in the lower right-hand corner. And you're now going to see a spindle chuck data button. So this is where we have our two chucks. And this is where you want to plug in those values that we just talked about. Now, you got a couple different options here. So I can toggle between OD gripping or ID gripping on either of my two spindles. If your machine is equipped with tailstock capability, where the sub spindle can also be used as a tailstock, you might actually get another option here, and you can show it what the tailstock is. So don't be surprised if you see these screens look a little different based on the style of commissioning your machine is. In our case, we're just trying to keep this pretty simple. So this is a straightforward main spindle, sub spindle scenario, and I'm not going to be worrying about tailstock or whatnot. But you know, these things can certainly change. Now, if it's a case where it's like a collet and the body to the base collet position is the same value, you don't have to have a number in here for the jaw projection. You could set it to 0. You just got to make sure that it knows where the front of that thing is, because the next step is going to be us telling it how far out the part sits, and that's going to be relative to this jaw face. Okay. All right. So we come in, we fill out our data, pretty confident on the size, and you can use the machine to measure this stuff too, by the way. Remember, as long as I have a qualified tool that I know the projection, I could come over, I could touch the face of Chuck. Since everything's based on that spindle face, I can quickly measure what that distance is. Okay, so now the next thing I want to get you guys, just kind of get your head around here. Bob asked if we can build a multi-chuck database. So what you could do is you could write these variables from a part program. So there you could, in theory, have a program with a bunch of different chuck geometries and just do like a go-to, or you know, you could put a little logic in to say, hey, I'm selecting chuck ABC or whatnot, jumps down and it auto-fills. So any of this stuff could be physically written to the system through a part program scenario. So that would probably be about the best way. The screen itself doesn't have the ability of selecting chuck A, chuck B, chuck T, at least not that I've ever seen. Okay, so the next step is we're going to kind of just talk about where we want the part to be in this whole process. So our part is going to be 100 millimeter blank. First operation we're going to do is going to be very simple. We're going to do a basic pick and place job. So not only do I need to know my part is 100 millimeters, but what is the distance that I want this thing sitting out of the main chuck when I work on it? And you know, it seems silly, but I will just hand draw whenever I start one of these jobs roughly what I want to be. So I'll just jot down, okay, this is the distance I want to be out from my work holding. And then when I go grab it, this is the distance I want it to be sticking out once I'm done with the transfer. So I like to kind of map that out. I might draw a quick little picture of the part and have that layout. But this all becomes very important when you start to fill out the program. Because a lot of stuff we're used to just leaving there for graphic purposes now become critical data when we start running this machine. So that's the layout of our chucks, basic layout of our part. The next thing is to kind of get your head around how the tooling is going to be configured. So I just wanted to show you a couple atypical live turret layouts. This certainly isn't the only one. There's probably a million different configurations of turrets when you get to these live tool scenarios. This is a BMT style turret, so this is pretty common. So I wanted to use this as a base example. It really doesn't matter where your mounting surface is, if it's on the peripheral of the disc, if it's on the face of the disc. It's really just understanding that the turret's going to be pre-datumed by the OEM, and then the offsets are going to be now relative to like a gauge line scenario. So you have two different style tools you would typically see in this scenario. We have a tool, most likely a live tool, where it's going to be plugged in to an adapter to a driven slot, right? So there's going to be some kind of hole on the face of the turret, and I'm going to slide that live tool in there. And the tool itself will be dead center of that datum. So usually in a case like this, the OEM will have set the turret reference relative to the driver of the live tool. So in my case, the dead center of this turret would be a 0 location. So from the tool's perspective, if I'm setting up this tool, I don't need to give any offset in my Z direction either way, but I do need to tell it an offset for my X. So here you see a quick little dimension A. That's the distance from the mounting surface. That would be the back side where this tool holder would physically touch, out to most likely my cutting edge. I didn't bother drawing in a tool in this little live tool example. But that dimension is what's going to get plugged into my length X in this scenario. So length Z would most likely stay 0, or if I had a little bit of inaccuracy in the holder, then certainly I could adjust it here. Now, normally in a machine like this, we're going to set these tools up one of two ways. Typically, they either have a presetter, So you're going to come down through the presetting routine. So the presetter will be datum relative to this reference point on the turret. But I'd like you to understand now, why am I getting these small positive offsets in my tool length? This is why, because everything's relative to these datums. Now, additionally, it makes it easy to be able to preset your tools offline. So I can go out to an external presetter, find that dimensional number, and just type it right in. So I don't have to go through and do the manual qualifying that I normally would do on a lathe. Now, in addition, I could have a live tool that's offset. So that could be a turning tool, a static tool, certainly a live tool, it doesn't really matter. But in this case now, there's two offset values that come into play. I still have that distance out from my mounting surface. That's my dimension A. And that's going to, in this case on a live tool, get me to the center of tool. If this was a cutting tool, it would probably get me to the tangency point of the cutting edge. But now I also have an offset, and an offset in the B, which is the Z direction in this physical turret. So you're going to see either a plus or a minus value represent B. So if you look at that left turret again, down here in pocket 16, there's looks like a Sandvik turning tool. So see, this is set up most likely to cut probably on the back, the sub spindle side. So I would expect to see a negative offset come in for this given tool. If I look at my boring bar, that's down a couple spots down. That one, I'm going to expect to see a positive value. And again, that number is most likely going to be the distance from the center of the holder out to that cutting edge, and that would be my B dimension. Okay, so you've heard me talk a lot. Why don't we get in and get into the mechanics of actually driving this program and creating some simple programs for it. So we're going to go in and we're going to do a very, very basic job. This process, this webinar, this has nothing to do with the complexity of part, all about the operation, right? The process. This is all about process at this point. So intentionally so, I want to do a very simple part where we're just going to machine a 100mm blank. We'll turn it from 100mm diameter down to 50 mil, and each of those steps are only going to go 40mm back. So there's going to be a 20mm gap in between the steps, keeping my part 100. I'm not going to worry about facing. We're not going to put any fancy grooves or anything in. This is quick, simple, down and dirty to get you to understand this transfer process. So we're going to go in. We're going to create a brand new program, as we normally would. And we're going to do this in ShopTurn. Now, all this scenario certainly could be done in G-code, but unfortunately, the cycle I'm about to show you doesn't have a G-code equivalent. So then you would need to get in and do a lot of this functionality with custom M codes, or M codes certainly provided by the OEM. So we're doing it all through ShopTurn at this point. So we'll go in, we'll start our program, and the first thing we're going to do is we're going to build our header program, or our header page, as we normally would. Now, the header is going to have a couple new pieces of information that become pretty important. The first thing is going to be the describe field. Now, if your machine has, or if you're used to lower technology lathes and you've seen describe, you've probably always been trained to leave it at no or shut it off. Because what describe does is it writes whatever value is in here to the physical offset. So it would literally overwrite the Z field for the G54. In a simple basic lathe, more times than not, that's the last thing I want to do. I did that all through the process setup. But in a machine like this, I know where all my values are. I can easily figure out where my dimensions are. So in this case, you might want to use describe, and then this way, if somebody goes in and changes an offset inadvertently, it doesn't matter, it's going to get rewritten anyway. So it's pretty common to actually use the describe here. Later, you're going to see also the describe function for the sub spindle, and there it becomes extremely handy because it actually does all kind of calculations for you to figure it out. Cylinder, retracts, machine tool change positions, these are all going to be pretty much the same thing you guys are used to. Now, in my case, I'm going to use the same tool change location. That's also going to be my safety location for my turret during transfer. Additionally, you're going to see we have our maximum RPM not only for our main spindle, but now our sub spindle. So the sub spindle can do everything the main spindle can do. Tapping, threading, as long as obviously they have an encoder feeding back off of it, which they typically always would. fully functioning. So that means constant surface feed as well. So that's why I need to have a max constant surface feed for that spindle. Then we have safety distance, same definition. But the other new area that you're going to see is the Z2W. And this is the retract location for the sub spindle or counter spindle prior to anything occurring. So first thing, start of the program, where do I want to send that sub spindle? So if she's staged anywhere else, it's going to move out, in this case, to 1,000 millimeters, which was the position that I decided to have my safe retract location. So at this point, why don't we start a program? So I'm going to jump into this ShopTurn, or in Sinutrain, and then go to ShopTurn. We're going to come up to Programs, and we're going to start a new program. And I'm going to call mine Sample 1. All right, so we give it a name. I want to make sure ShopTurn is selected, because we're going to do this conversationally. We say OK. So now let's start to go through the page and build it. So if I look at my diagram here, again, the layout, I know where I'm setting the machine. Now, I have some dimensions here that are preset. I'm going to leave the describe function off for now, and then we're going to add it in a little bit to show you the difference of what it does. But since I know this distance, if I wanted to, and I wanted to auto-fill out, I could say describe, and I can plug that number right into here. So let's leave it at no for now. So it makes me have to set this work offset prior to running the part. Cylinder blank, 100 mil. I'm not going to leave any material for finish cut in this example because I'm not coming down and facing it. If you did, that's certainly okay. This transfer will take account of all that. So you can still do the process like you normally would. Now in our first example, remember we said we got a 100 millimeter blank, but I only want it sticking out from the jaws out here by 60 mil. So we see that dimension line in that lower section of my part. So that's where these numbers come from, and it's important right now because this isn't just for graphic purposes. It's going to use this when it does the handoff. We're doing a simple retract, whatever I want for my retract value. I'm going to move to a safe location, machine coordinate position, and it's going to a 500, 500. So again, remember this retract location that we talked about, that could be used as my tool change location, and I'm also going to use this as my safety location during my part transfer. We got some max RPMs, 2,000 spine, safety distance, how close do I get, and then I come down to my Z2W. So again, where do I want to send that sub spindle? And this could be anywhere. I don't have to send it all the way back to the extent of its travel. Maybe I got a real long bed length, but I'm doing some smaller work with the sub spindle. It's okay. Just understand your offsets are going to be relative to this location, right? Okay, so you fill out the page, hit accept, program has now begun. So if I look quickly at our PowerPoint here, the next thing we're going to do is we're going to just do our first operation. So it's just important that I select a tool that was set up to work on the main spindle. So you're going to start to see we're going to have tools that kind of bounce between both spindles as far as if it's a left-handed or a right-handed tool. And then from there, it's just going to be a basic turning cycle like we've used plenty of times before. So let's go add this cycle in, because once the cycle's there, then we can come over, grab our part, and handle the transfer. So for me, I'm going to just go to our turning, stock removal, and we're going to fill out this page. So if I go to select tool, and I'm going to go all the way back to the tool list, you notice I'm going to use a tool up here, right, that has been set up as a left-hand tool. That's important because that's the tool that can run on that spindle. So if I'm taking the same routine and I'm running it between main spindle and sub spindle, this is about the only thing I'm going to have to change, is which tool I'm selecting, because the mirroring is going to handle all the dimensional data for me. So later, we're going to do some back turn stuff, and there you would see I would use a tool that was qualified for back turning, or shall I say, a right-hand tool for my sub spindle. So in this case, I'm using tool 1 to program, give us some feeds and speeds as normal, got my dimension. So as I mentioned before, we're starting at 100 mil blank, starting at Z0 because we're going to say this part's already been faced. I'm going to machine it down to a 50 mil diameter and back 40 mil. That would just take 10 mil per cut. So as far as the graphics would look, it's going to be very, very simple, very traditional that I would see. We just get a cutter come in to the main spindle, take a few cuts. Great, we have our part. Again, here you see, if you look at the dimensions, the overall blank, 100 mil, and it's sticking out from the jaws 60 millimeters. So all this is typical. Now it gets fun, because now we get to add in the sub spindle. Okay, so what we have, and what we're going to see here, is under our various button, we have a button called Counter Spindle. And Counter Spindle is what's going to allow us to manage and handle that sub spindle that we're using. So the first field that you get when you go into the Counter Spindle button is the Complete Acceptance, Machine Face, Draw, or Grip option. So I typically will use the Complete Acceptance, and what that's saying is it's going to handle all of the steps of grabbing and transferring the part in one shot. Now, let's say for argument's sake, I wanted to just drive my sub spindle over and grab my part. But then I want to come down and do some different machining ops, because maybe I wanted to support it by the sub spindle for a little while. Well, I wouldn't do a Complete Acceptance yet, so you can break these things down into individual operations. So I could do a grip, and that would just bring my sub spindle over. So you see the expansion of this selection gives me grip, draw, machining face, or Complete Acceptance. So we're going to concentrate on Complete Acceptance, but just keep that trick in mind that you can come in here and you can pick individual operations too. So I can simplify the functionality that she's about to do. Next option down is going to be my main to counter spindle. So this is my transfer strategy. So as I open up this field, I can decide, well, where's my part? It's viable that my part could have started in my sub spindle and being transferred to the main spindle, especially if I'm just using this as like a little chucker operation or whatnot, or pick and place. So you want to tell it where it's going, where it's coming from. So in this case, we have a part sitting in the main spindle and getting transferred over to the counter spindle. Next option down, where do you want to go to that safety location during the transfer cycle or operation? So this works the same way as our safety retract for tool change. I can tell it machine or work, and then my offsets would be relative to that. So in this case, I always like to use machine. It's a constant known value. It's independent of all offsets, so I can be absolutely sure I know exactly where that physical turret is prior to doing the transfer. You have an option for chuck flush, yes or no, and that's just coolant. So if the builder equipped the machine with a flushing option, it'll flush coolant down the sub spindle jaws or the main spindle. And what it's going to do is it's going to clear out any chips. So you don't get any chips that get in there during the transfer process and obviously affect your clamping and your accuracy of your part. So that's just a simple yes or no scenario. Now, when you get down to direction, this is what do you want the spindles to be doing during the transfer. So you got a couple options. You can have the spindles at off, so it should just come over with both spindles in a stop state, grab the part, and then bring it out, and then she'll fire up on the next operation. Or I could have my spindles physically running. So in this scenario, I could then tell them what direction I want my spindles to be running in, and she'll do the transfer fully live. So simplicity's sake, we're going to first do our transfer here without my spindle running, but they certainly could be. Next field is our little A1, alpha 1 field, and this is an angular offset. So this is important if you have jaws between the main and the sub spindle that could potentially collide during transfer. So what you want to do is you're going to want to put some kind of an offset between those two jaws, and this is that angular value. Now, you may not know if both spindles are at 0, if those jaws could collide, so that's usually the first thing you kind of got to figure out. But then once you know, you can put some offset to them. So potentially you could have the two jaws nest within each other during the transfer process, and that's perfectly fine and actually very typical. But that's what this offset comes in. Okay. Now from there, we then got to look at where is the physical subspindle going. So this is really kind of where the rubber hits the road. So Z1 is an absolute position relative to your G54 or whatever work coordinate is set to the main spindle. So the system, because it knows all the chuck data and projections, will automatically bring the sub spindle over and grab the part. And what it's doing is it's saying, I'm going to take the jaws that I know where they are. That's why it's so important to get the jaw information accurate. And I'm going to slide it over top of that part by 20 millimeter. So I'm going to expect to see the jaws grabbing this part by 20 millimeter when I'm all said and done. So again, absolute value, Z1, absolute value from the face of the part while it's in the main spindle back to where you want the jaws to stop and grab the part. Now, this sub spindle is going to come up at a pretty high rate of speed. Some of these things are commissioned to boogie, so to speak. So I'm probably going to want to slow this thing down before I actually stop and do the grab. So in that case, I can do a feed reduction point. So this is a distance, my ZR, and this distance could be incremental or absolute. That's up to you. It's still going to be relative to the part in the main spindle, but this is how far away from my stopping point or my clamping point do I want to start slowing down. So right now, I just left an incremental value, which is what I typically use. And it's saying, hey, 50 millimeters from the -20, I want you to slow down to 500 millimeters a minute. So once you've achieved it, you can clamp. So what that means is, what I should see is I should see when the chuck jaws are 30 millimeters to the plus of the face of the spindle, she's going to slow down and then move at 500 millimeters a minute until it gets to the -20, and then do the grab. So that's what those three values are. A little tricky if you don't have somebody displaying them in that kind of detail where these numbers are coming from, but I think once you see it, it makes perfect sense. Okay, now we do have an option, travel to fixed stop. So what will happen is, in this case, the sub spindle is going to come in, it's going to go to grab, and it's going to keep putting pressure on the main part. So that's pretty common. A lot of times if I'm using it during machining operations, maybe not just for the transfer, I want to keep a positive pressure on the part at all times. You can use the fixed stop mode. Certainly used a lot when I'm using it as a tail stock. Now the next two options, my draw blank, cutoff cycle, we're going to go into them later on the webinar, so we're not going to worry about them now. Then I need to tell it what work offset I want to use once the transfer is complete. So this is my opportunity to pick my G55. Now, we can do a describe here and let the machine calculate where the part is sitting in the sub spindle and write the appropriate work offset, or I can have preset that work offset. So the first time we do it, we're not going to use any describe, and then we're going to rerun it and show you what would happen otherwise. Then my final question, where do I want to send the sub spindle when the transfer is all complete? So it's not normally going to go automatically back to where it was from the header page. It's up to you right now to tell it where you want her to go. So that would be my two last options, my overall dimensions of my part, and then my retract position. And then the ZV, that could be an incremental value or an absolute value. Now the absolute value, no calculations are going to be done. It's just going to write the offsets directly. But if you use incremental, then it'll calculate this number. Okay, so what is the transfer going to look like? So we're going to machine the part. She's going to come over, you see in this second view, to 30 mil in front. Then it's going to move 50 millimeters incrementally till it gets to negative 20 millimeters on the part. Jaws will come down and grab it. And then in our case, main jaws will open, she'll retract back, and then I'll be able to do something on that sub spindle. So let's go make this happen. So we're in our program. It's time to get to this screen. So I want to go to Various, and I want to pick the Counter Spindle button. It's the vertical soft key right up here. I can go through each of these options. So remember earlier I did say if we wanted to just come down and grip, because we're going to maybe do some operations for a little while. Maybe I want to draw my part out. There's a bunch of different things I can do. In my case, I want to do a complete acceptance. What's my transfer? Is it going from the main to the counter, counter to the main? So there you see the part flips. Where do I want to send the turret to a safe location, and what are those values? So she's going to be sitting here during the transfer. Coolant flush, spindle direction, whether I want my spindles to be on or not during the transfer. If I need to orient my jaws, as I mentioned. And then how far onto the part am I going to grab before it pulls back. Reduction point, feed rate, all like we said. I don't want to worry about coming to a fixed stop. I'm just coming on, grabbing it, moving back. Draw, cutoff we'll use in a minute. And then what work offset am I using on the back? So right now, I'm going to leave this at no. And where do I want to send my sub spindle when I'm all said and done? So you fill out the page, hit accept, it's going to come in as a singular event. So if we start to simulate it, now you're going to see that we're going to get our turned operation, and then our part's going to transfer over to the sub spindle. So if I zoom back and pull it back a little bit, there you see our two spindles, nice little view. So she turned, came over. There's your 20 mil that's coming on, and you see how the 0 is lined up right there. So that's my full transfer. Okay. So last thing we want to do is add a little operation here, and then we can run it, and then we can show you how the describes start to work. Okay. So final feature, final field we're going to do is we're going to, oops, if I go to, there you go. Okay, back to the PowerPoint slide. Final field we're going to do is we're going to work on the sub spindle. So again, important that we have the mirroring set up in the work coordinate level, or work coordinate that I'm using for the sub spindle. And the only thing I got to do here is remember I got to pick the correct orientation of tool that can physically cut on that spindle, or it's going to tell you that it can. But you notice the cycle itself, I'm still using negatives because the mirror handles all that. So if I have common routines bouncing between them, I can do all that. So the cycle we'll insert there, and then we're going to do some cutoff. Okay, so let's put the last cycle in. So in this case, I'm going to come in. We want to grab our tool that's going to be machining the back side. Now, in this case, since it's the exact same dimensions, I don't have to change anything else. And it's going to allow me the final operation on the back side. So we go simulate. She starts up. She's machining. I'm going to zoom back. There was our transfer. Happened a little quick. I could certainly slow it down. But you see how we can now start to move back and forth. It's running out to that safety position. All right, that's our safe location as it's cutting our part. Okay, so let's run this and start to see what's actually going to physically happen in auto mode. So remember, I have everything off right now as far as the describe functions. So it's going to be totally on me to make sure I come in and I give it the appropriate offsets. And I'm just throwing in some simple offsets here. And remember to put the mirroring. I got to do all of that. So in this scenario, what you'd have to do is you'd have to pre-machine part 1, let it do the transfer, and then probably stop it, then go qualify and find the backside, set that work offset, and then continue on. And that's a pretty common scenario that most people that have been running sub-spindle machines are used to at this point. Once you see the describe, you'll see that that is no longer required. So here I can come to auto. We can run this part. Comes through, runs as normal, does its transfer. Now I'm back. So if I'm running, and we'll do a little single block. So I'm doing my cuts. Now I'm going to do the counter spindle transfer, right? So if I look at my axes, Z2 is still at 1,000 millimeters. The machine is going to auto-calculate where it had to go. It figured out that it had to move to 355 millimeters, but that's going to be based on the work offset that I wrote and the appropriate chuck dimensions that I have. That's why they're so critical. So it comes down, grabs my part, That's my feed on. Now it retracted back. Spindle starts back up from the second operation. Remember, during that whole process, spindles weren't running because I told them to be at a stop state. Finish it up, and it's going to cut the other side. So, same scenario like you just saw in the graphics. This would be in run mode. There's our transfer, comes back. Now, you see how, let me show you this. You see how, when it was all said and done, it's not lining up right. Well, that's because the offset I put in is not accurate. It won't work based on all the dimensional data I have. So everything's being staged in the wrong spot. So that's why it's critical that if I look at the offset stack, I have the right value. So if I was to do the math real quick and look at it, if my sub spindle is sitting 1,000 millimeters away, I have an 89 millimeter chuck body, a 51 millimeter, 51.625 millimeter jaw projection, and then the part's going to end up sticking out, I would have needed to put in a value of 779.375 millimeters. I just threw a dummy number in here, 750. So your numbers still have to all make sense. You can't just stage this anywhere in space because there's no way that that could actually occur based on its known dimensions, right? Based on its known chuck dimensions. Now, what you can do here is you can let the system calculate some of this stuff. Now, the one I have to know is I do need to know where my starting plane is. So I see this 200.625. That's a critical dimension right now. So if I go into the program and I open it up and I turn it on describe and I give it my value, now I can also come back and tell it to do a describe. So in this describe, all I need to tell it is what is the overall part size once I've done the transfer, right? So it knows how far in the part is from the grab, 20 mil, and I know that my final part dimension is going to be 100 millimeters. So that's how far it's going to be sticking out when it's done. By turning these two variables on, when I go to run the part program, if I'm looking at my offsets right now, cycle start, it's running. You see it wrote that value, and it even wrote, now this one wasn't a direct drop-in. It calculated it. So it calculated the number of that work offset by knowing where I'm going to, what the appropriate body was, what the jaw projection. So if I went in and, let's say for argument's sake, reset this, I had put the wrong number here, right? 50 mil when I set it up, and I go to run it. We'll leave it on the offset table so you can see the calculation. We start running. See how it calculated out a totally new value. So those numbers are all dependent on you setting this value appropriately. So in my case, 89 millimeters. Now, what's cool about this is, let's say I forgot to do the mirror. And I'm just going to zero out a bunch of this stuff. So first article run, I don't have to know anything about where the sub spindle is, as long as I know my work holding. So when I run my part, it's doing its thing. When she gets to it, not only will it calculate it out, since it knows it's on the sub spindle, it automatically sets my mirror for me too. So I like the describe function. Main spindle, 6 of one, half dozen of the other. I may or may not always use it. Sub spindle, I always use describe. It's the easiest way, cleanest way to start handling these transfers. Okay, so we got a couple other ops real quick to do before we start to wrap up our webinar. And really the next step is, what if I want to deal with part off, right? Don't always have the luxury of being able to pick and place my part. A lot of times, most of the time, I'm working from some kind of a bar. So we have a couple of other add-on functions. So here I can come in and I can do my part off cycle. Now the previous screen, this is just going to be what I have to modify in the header cycle to manage this. So my setup's going to be slightly different. Certainly my overall part length is going to be something significantly larger. So I threw 500 millimeters in here. But in addition, I'm going to have my position of my part sticking further out. Because remember, I got to get a part off blade here. So this part's got to stick out at least the part length, plus some clearance and plus a blade width. So in my case, I'm going to tell it 120 millimeters it's sticking out. Now, you might say, well, what if I want to be able to draw it out and then part it off for rigidity's sake? Well, that's coming next. That's our last cycle. So in this case, this is a very simple, traditional part-off cycle. Come over, grab, part off. So we're going to modify the program. So I'll just copy it and paste it. And then we're going to add in our new feature, which is cutoff. Now, it's real simple from the transfer cycle perspective, or the counter spindle cycle. I just turn this on in yes. But what it does is it now gives me my little open-ended bracket. So any of you that are used to getting to a cycle that needs a little more information, you always get the little open-ended bracket. So now I can associate a cutoff cycle to the counter spindle. And this isn't fully order of operations, think about it now. So now I'm in the counter spindle, and in the middle of that, she'll jump down, run the cutoff, and then return back to the counter spindle to do the retract, and then continue on. So you just got to know that that's how I'm going to handle my cutoff, and that's how I can give my dimensions and everything for my cutoff. So at the end of the day, it's going to look a little different because my part's going to be sticking out further. It's going to be sticking out 120 mil. But my transfer is going to be all pretty consistent until I get to the cutoff. So you're going to see I'm going to be on my part with the counter spindle supporting it while I come down, part off. What's nice is the system will automatically do a pullback before it retracts the blade, so you're not dragging the blade up the part, and then she'll do the retract to the safety location. So for us, we don't have to spend the time rewriting the program entirely. We can just copy and paste it. We'll call it sample 2. Go into sample 2. Now, as we said, we want to now tell the machine that I have a lot more material here, right? Because I got some bar, and I'm sticking out further. I'm sticking out 120 mil. So there's my minus 120 millimeters. Other than that, everything can stay exactly the same, assuming you want the sub spindle to go to the same location, all that kind of stuff. All right, I hit accept. We have our primary operation stays the same, but now we're going to come into our complete, and I got to remember to tell it, yes, I want to use a cutoff cycle. So just the nature of clicking yes, got our nice little animated graphics here, shows you what's happening. But the nature of saying yes now gives you this option. So if I try to run something, she's going to tell me I don't have sufficient information. I'm missing my cutoff cycle. So in our case, we're going to go to turn, cutoff. Now I pre-created the cutoff cycle here earlier, so we don't have to worry about it. But I'm using a plunge cutter. If I look at it, this one was 300 millimeter insert width, or 3 millimeter, shall I say, insert width. Obviously, whatever dimensions you're using for your cutoff tool. So we give it our basic dimensions. If you guys have ever used the cutoff cycle, which I'm sure you have, it's the same exact scenario. Where do I go? What's my retract, my safety position? Now, a lot of times I won't necessarily do a slowdown because I don't have to, right? It's not like I'm worried about this thing dropping off into a parts catcher. It's going to physically be grabbed by my sub spindle and move back. So you don't have to do the reduction. Sometimes I'll still maybe drop down my feet a little bit so I'm not pushing too hard when it breaks through. But you can go much more aggressively, obviously, in this scenario. So we attach the two cycles. So now, if we start to look at it, you can see that we're going to get we see the part off cycle. The whole thing's sticking out further. There's my part off. Then she moves back. We get our secondary operation. And while everything stacks, everything makes sense for us. So it's really quite simple once we get to the part off, as you start to see. The big trick is just getting that initial setup. Making sure you know where everything lies dimensionally. Then all the numbers make sense. If not, you're just chasing your tail. So if I was to run it again, since all the offsets are really the same in this case, I'm not going to see any change. What I would need to change, obviously, would be my work coordinate. That's going to be moved out further. So if I do my math, my 89, my 51, I add another 120, that would be my work coordinate of the part. So that's the only thing I would have to reset between these two scenarios. And then our final operation would be the draw cycle. And the draw cycle is really nice because what that's going to do is that's going to allow me to keep my part stubbed up nice and short, so I just project out as much as I need for my machining op, and then when I'm ready to, it's going to pull the bar out, and then I can part it off, and then I can do the transfer. So in our case here, the only thing I have to change is my projection distance. Right, so I'm going to shorten everything up. I'm going to bring it back to my 60 mil, but I still got a big long bar in it. From there, I have an additional option, which is called draw. And the draw, I'm going to tell it to turn on, so I want to draw. And then I'm going to give it the feed rate. Oops, sorry. I'm going to give it the feed rate of the physical draw. So that's the speed that the sub spindle is going to be moving as it drags that part out. So a lot of times I don't want to do that. Obviously, it has a very high rate of speed, especially if I have a pretty long bar in or whatnot. So that would be this feed rate right here. And this is going to do a bunch of calculations for you. I mean, this is literally all we have to turn on for it to handle this draw. So what's it going to look like? Well, in this case, you see the part-off cycle. That's way back inside the spindle. So we're going to come down, we're going to machine, and then we have to move over to our reduced feed point, feed on to the 20 mil. I haven't changed any of that strategy. But now the system's going to do some math here, do a little calculating for you, as far as how much it needs to draw this out for the part-off cycle. Then cutoff's going to come down, cut it off, bring her on back, and machine the backside. So let's try it. Okay, so for simplicity's sake, we can certainly copy sample 2, paste it. We're going to call this sample 3. And we can modify it up. We can talk about it a little bit. Okay, so as I said, this is going to give me the opportunity to start to shorten everything back up. So I'm just going to go back to my 60 mil. So that means my 206.25 value is actually accurate again. That is correct. Everything else is going to stay the same. Now in this case, we want to just come on down to my counter spindle and give it the draw option. So just say draw yes, give it some kind of feed rate. So I'm going to maybe run 500 millimeters, pretty slow feed rate in the metric world. And then I'm just going to hit accept. So if you look at it, and we let the animation pop up. Yeah, it's acting slow today. But anyway, Chuck's going to come down, grab, do my draw. Here you go. There's your draw. Once the draw is complete, then my cutoff cycle is going to come back over and come into play. So just by adding the draw, we save it, and now we can start to simulate it and see what it's going to do. All right, so I'm going to slow things down a little bit, and we're going to rerun this. So there's your backside. Oops, that's my zoom. Okay, I want to just slow things down a bit, and we're going to talk about this. Okay, so you see I'm sticking out my 60 mil. My sub spindle comes over, grabs, that's my draw. So the big question usually is how does it know how much it's going to draw, right? How far back it's going to go? I wasn't asked that question anywhere. Well, if we look at it again, and I'll single block it here in a, oops, hitting too many buttons. Let me start over, sorry. Okay, I'm going to single block in a sec. So we come down, do a little turning. All right. So go to our retract location. Sub spindle is going to come up here in a sec. That's our slowdown point. Now she's going to come over, grab, and pull. So how far out did it pull? Well, it knows that you told it the part is sticking out 60 millimeters in the header page. So it knows it has to pull it out 60 mil. There's nowhere else it could pull it out to, right? Because then it's not going to be consistent. So it starts doing that calculation for you. So that's how it knows. So it's going to pull it out to 60 mil, and she's going to come down, fires up the chucks Now I know we had said in the cycle that they weren't running, but certainly since it sees that in the cutoff cycle they have to be running, that's going to supersede it. The chucks will fire up. Here we're going to come down. It's doing our part off. So there's my little corner break. Feeds down to my reduction feed point. Comes across. Now this, if you watch, it might be hard for you guys to see, but there's your pullback. So if I zoom in, you see the gap in the insert. I'll zoom in a little bit more for you too. So what it did was she immediately, when it broke, pulled back to Sub Spindle, and then even moved the part off blade just off that surface, so it centered it between this gap. And then from there, she's going to pull it straight up, and we can zoom back out. Okay. Sub Spindle can run on back to its safe spot. Then I can take it out of single block mode and finish up the job. Zip, zip, zip. And there you go. All right, so we got a lot of stuff here from my PowerPoint slide. This would be the end of the primary presentation. So as always, we want to open up to any questions. We had a few come in. I grabbed a few while I was talking, but we can scroll back and see if there was maybe a couple I missed. I think this one might have been already answered, but I'm going to read it real quick. This was from Jay. Let me pull down my window here to see it. Okay, so this is Jay's question regarding the force of the sub spindle. So he said maybe this is a tailstock function, but can you set the force low on the tailstock and gently but against the main spindle? I've seen it done on some lathes before. I did not know the standard. So and then I think we were talking about the move to fixed stop mode, and that's why I think he said, aha, okay. But yes, this is a nature of that fixed stop function. Now, in ShopTurn, the force is predetermined by a machine parameter, but you can program that externally if you want. A lot of this gets left up to the OEM, how they want to set it up. I've seen a lot of OEMs will do custom screens for you to be able to define the force that you want. Some guys will fix it to the same value all the time. You know, that kind of stuff. It's really kind of up to them. We got another question. Do Siemens lathes have inverse time G93? I know that in some more milling oriented, but is this a lathe? What is it? Is it a lathe question? Okay, so inverse time, which is certainly a milling function, a multi-axis function. It is supported in turning, but more typically it would be supported in the turning if I had a machine that's going to do 5-axis type of tool path. I've never used inverse time in more of a traditional turning type of tool path. But the nice part about our controls is you don't have a lathe control, you don't have a mill control. You got a control that has both technology in it simultaneously. Specifically the 840. I can walk up to any 840, change a couple parameters, and make it think it's the opposite technology. So all the functionality is really there on both of them. Okay, what else do we have? A couple other questions came in. Let me browse through. And as I'm reading these, if you guys have any other questions, please feel free to type them in. We got, yeah, can we use G291 mode? So that's going to be dependent on the OEM. So like to give you an example, if I jump back to this machine, and I go to the offset table, when guys ask about 291, that's our ISO compatible mode. The Siemens control is always a DIN ISO kind of hybrid, meaning we do recognize and read G1s, G2s, G3s, that kind of stuff. But we also have a compatibility mode that allows us to stay in pure ISO, which is really FANUC protocol. So drilling cycles and whatnot, that's what's called our G291 mode. Now, it's dependent, and the easiest way to tell if a machine was set up for it it needs to have an H column here in the offset table. Because if you think about it specifically from a mill perspective, but we do the formatting looks the same between a lathe and a mill. In a mill, you use a G43H number to call up your tool length offset in the FANUC. Because of that, we need an additional H column. So if you want to know if your machine supports G291 mode, look to see if there's an H column here. If it's here, mill or lathe, it does support it. Now in the lathe, it's important that you pay attention to this. In the lathe, FANUC actually has 3 different protocols of G-code. And a lot of people don't realize this. You know, a lot of people think, oh, it's a 6M or it's a 6T or a 0T, it's a 21I. That doesn't mean anything. In just about any of those FANUC controls, there's a machine parameter, and you can switch whether it's reading an A, B, or a C protocol. And if you don't know what you're used to, do a little digging. Go to your FANUC manual. You'll see that there's 3 different protocols. It has to do with what does the threading cycle look like. A 2-line G76 cycle came out in FANUC B. FANUC A used a different for threading cycle. I don't know all the cycles because my shirt doesn't say FANUC. But it's important to know that, and I bring that up because if you're going to run our lathe controls in the ISO G291 mode, there's a machine parameter that sets that protocol. So we support all 3, but you better set that machine parameter up in our control or you'll run into compatibilities because FANUC has 3 different protocols. But great call, great question. Give me a sec here. Okay, I was asking about fixed stop. I think we explained that enough. I hope so. Can you also perform an operation like this using a G-code program? Okay, so probably referring to the transfer. So yes, you can absolutely do the same style transfers, but there is no CAN cycle set up for it. So it's all going to be on you. Some OEMs will set up a custom cycle to handle it. But a lot of other ones are just going to build it as you're going to handle each of the discrete steps. So you need to know all the M codes that are going to trigger chuck open, chuck close, synchronize. So we'll do one of these webinars on the G-code side in the not so distant future, just so you can kind of see that. How would we distinguish the spindles in our program? Oh, I'm assuming you're talking about from the G-code side. I'd say that the best scenario there, go back and take a look. I'm pretty sure I did a multi-spindle webinar for G-code. But what happens is you get some set main spindle commands come into play when you're jumping between your spindles. There's some slightly different protocol where you map what S code and M code goes to what spindle. So you have to know the number of the spindle. But I did do a webinar on it, so check it out. I think you'd find it quite helpful. Okay, so Jay's asking if we have a 45-degree flat for a live tool, can we use ROTS and trans commands to establish a plane? Absolutely you can. Additionally, if you happen to be fortunate enough to find yourself on a machine that has Cycle 800 commissioned, you'll actually get a swivel cycle, and this one was not. That's going to be a great question when I get to the B-axis scenario, because that's where you get into that kind of stuff a lot. You know, to have a fixed turret lathe doing compound features like that, you would need a holder that's now cantered at that position. It happens. You can buy them. Certainly in a case like that, you could use the rotate commands to do that. Okay, let me see. We got a few other questions. Guys got a lot of good questions today. Oh, here's a good one. Does the part-off cycle take into account the tool width? And yes, it does. So when you saw the draw function, when we were drawing out the bar and then coming down to part-off, you know how it automatically calculated it had to pull out 60 mil? Well, actually pulled out a little more than 60 mil, right? Because it had to accommodate for the width. So it added that extra 3 millimeter. Is it possible to have the draw length too short and cause a crash? So no, again, remember, it calculated the draw length for you. So as long as, if you made that length shorter when you created the program in the first place, you would have crashed before you ever got to the transfer. How can I figure out where my chuck orientation is? This is a good question. So we talked about that one little feature, right, where I can do an orientation angle right here. Well, step one is, how do I know if my jaws are going to collide, right? I mean, these chucks, when they get bolted on, some of them have drive keys, some of them don't. But even if it has a drive key, we don't necessarily know that spindle orientation 0 on the main and 0 on the sub are going to have those two jaws lined up. So there's a bunch of ways you can do it. Simplest way, just come out to jog, go to your TSM screen, go to your spindle, and put it to position mode. And here you can position each spindle to 0. So first I do S1, then I do S2, and then I could just manually jog up the sub spindle. I can see where those two jaw work holding orientations are, and then you can figure out how much you need to adjust that position. But yeah, don't assume that just if they're both at 0, 0, they're going to collide. There's no way to know. You got to look at that specific machine to see where they all are. And then certainly if somebody removes a chuck and puts it on, if there's no drive keys, potentially they could have it positioned another couple bolt hole patterns away, and then everything's going to change. So if you're swapping out your work holding, make sure you check that. For example. Okay, so there was a question regarding higher level commands like DMG uses a clamp B1 for clamping the option. Question is, are there any standard lathe commands like open chuck or close chuck? So no, you would need to, from the G code perspective, you would need to know the M codes that the OEM assigned to it. We don't know, or I don't know of any universal commands for driving that chuck open, chuck close, because it's really up to the OEM. Now, what happens in the back end is there's some commissioning steps they do that basically tell ShopTurn what those M codes are. So ShopTurn, it has to be set up the right way too, or that won't even work. Can you get swivel cycle on a y-axis mill turn lathe? Absolutely. Absolutely. And in fact, it's very common with a B-axis on that, because you can also use it for your align tool plane. So that's yes. Is it possible to use sub spindle along like single spindle? If yes, which setting we need to activate? Is there enough? Only mirror. Oh, okay. So if I read this properly, you want to be able to just basically run the sub spindle as opposed to run the main. Yeah, it's really just use the work offset. That's mirrored for that. And then let's see if this one had it here. Some of them give me the ability of telling it which spindle I'm working on here. Now, in this case, you would just pick the appropriate work offset, and it's automatically going to drive to that sub spindle. So yeah, you can use the sub spindle by itself. You don't have to use the main. That was also why we had that transfer option of sub to main, main to sub, or sub to main. You could start from either one. I mean, two spindles work two different parts without making transfer. Yeah, absolutely. I mean, nobody says you couldn't be jumping between the two parts, and then you're probably at that point you're using it as a glorified chucker machine, but you're chucking in the parts, so you're going to stop after the program cycle. So the question again was, he wants to be able to work on two different parts on each of the spindles. Just jump between the two work coordinates, and then you can run any tool path you want there. But keep in mind, think about that stack position. It's important that the offsets get set properly. Okay. Boy, I think I got them all. I may have missed a couple here. Oh, we got another one came in after. Oh, ask a question. Yeah, Jay, just give me a call after we get off. I'll be happy to talk to you. And other than that, I think I got everybody else's questions. If I missed anything, again, as I said before, let me jump back to the PowerPoint, you can always shoot me an email, and I'd be happy to answer any further questions. From my side, I'm going to stop the recording now. Thanks again for hanging on with me. All right.